In this video, we will learn about motion diagrams and also how to determine the signs of position, velocity, and acceleration. First, let us learn about the position vector. Suppose we have an object in the xy plane, which is at this point. The position vector stretches from the origin to that point. It is usually denoted by the letter r. So the r vector is the position vector and points from the origin of your coordinate system to the position of your object. Suppose this object is moving. Then at the initial time, say it was over here, and at some later time, it was over here. So we can talk about the position vector at time 1 and the position vector at time 2. The change in position is denoted by delta r, and it points from the initial position to the final position. To repeat, r is called the position vector, delta r is called the change in position, or is also known as the displacement. Notice that delta r is r2 minus r1. Let's see how that works. The effect of delta r is to go from here to here. We want a combination of r1 and r2 that has the same effect. So we start from here, and first go to the origin. That will use vector minus r1. And then we go from the origin to the final point, and that is vector r2. So in other words, minus r1 plus r2 has the same effect as delta r. So delta r is r2 minus r1. Notice that this vector, which points from the initial point to the final point, is given by the destination position vector minus the initial position vector. All right, so final position minus initial position gives you the displacement, and the displacement vector points basically in the direction that the particle is moving. Now that we have learned about position and displacement, we can talk about the rate of change of position. That is, how position changes with time. We define the average velocity over a certain time period to be the change in position divided by the change in time. And this gives the average velocity over that time period. If we now shrink that time interval, this ratio, delta r over delta t, eventually becomes the derivative dr over dt. This process of taking the limit is something you will learn in calculus. You can also refer to some of the background slides available in Sakai. So we say dr dt is the rate of change of position, or the derivative of position with respect to time, and that is called velocity, and it is also denoted sometimes as r dot. The dot on top simply refers to taking a time derivative. Here are a few key points to remember. 1. The change in position is a vector, and so is the velocity. Since dividing delta r by delta t does not change the direction of delta r, but simply scale it and change the units, the direction of delta r and the direction of the velocity will be the same. Once again, let me repeat. The direction of the velocity will be the same as the direction of delta r. The difference is simply in the units. Delta r would be measured in meters and velocity in meters per second, and in the scaling of the vector. But the direction would remain the same. Derivatives may seem mysterious, but you can always link them back to this simple ratio of changes. Just as velocity is the rate of change of position, we can talk about the rate of change of velocity, and this is called acceleration. Once again, we can refer to acceleration as v dot, where the dot simply indicates a time derivative. Now we move on to motion diagrams. A motion diagram is simply a series of numbered dots that show you the position of an object at consecutive moments of time. You can think of it as taking snapshots of the motion of an object, or watching something move under a stroboscopic light. In this example, we see that as the time progresses from 0 to 1 to 2 to 3 to 4 to 5, the position changes. And it changes in a very uniform manner. The spacing here is the same as the spacing here, the same as the spacing here, and so on. What information can we extract from this motion diagram? We have been given the positions and the times. Now we can draw arrows linking consecutive dots. This arrow is delta r01. It shows you the displacement from position 0 to position 1. But we have said that the direction of the displacement is the same as the direction of the velocity. So this arrow can also represent the average velocity during the time interval between 0 and 1. Similarly, this arrow represents both the velocity between times 2 and 3, as well as the displacement between positions 2 and 3. We notice that the lengths of the arrows are constant, and we notice that the direction does not change. As a result, the acceleration, which is the rate of change of velocity, is 0, because the velocity does not change. Remember that we should look at both magnitude and direction. The velocity maintains the same direction and the same magnitude or length. And so there is no change, and the acceleration is 0. Another way of finding the acceleration is to view it as the difference between two arrows. The acceleration at this time is given by this vector v12 minus this vector v01. But since there is no difference between these two vectors, subtraction gives us 0. Let us look at another example. In this case, the spacings are not constant. Drawing the arrows connecting consecutive points, we see that the velocity arrows are shrinking in size. However, the direction does not change. What about acceleration? Once again, remember that acceleration is connected to the change in velocity. So the acceleration at time 1 will be the velocity after minus the velocity before. if we take the difference of these two velocities, we see that the acceleration must point to the left. Another way of thinking about it is, what arrow should I add to this initial velocity to get the velocity afterward? Since the velocity afterward is smaller, to reduce this arrow, I need to add a small arrow to the left. And indeed, that is what we see, and I carry on this procedure at each point. Again, the acceleration at 2 is this velocity, which is the after velocity, minus this velocity, which is the velocity before. We can see that the object is moving to the right, and the acceleration is pointing to the left. Because they are pointing in opposite directions, the speed of the particle is decreasing. That is, the length of the arrows is getting smaller. Here's another example. This time, the particle is moving to the left. Pause the video and take a moment and try and draw the velocity arrows and then the acceleration arrows. Try and do this by yourself and then move on to the next slides to see the answers. I draw the velocity arrows, and we can see that up to here, the length of the arrows is increasing, but the length of these two arrows is about the same. So, what do the accelerations look like? Since the length of the arrows is increasing, the accelerations must be pointing in the same direction. Again, we can find the acceleration by taking the difference between two consecutive arrows. For example, over here, v34 is longer than v23, and so to get v23 to be the same length as v34, we add a small acceleration pointing to the left. Again, to go from v34 to v45, we need to add a small acceleration pointing to the left. But v45 and v56 are about the same length, and so the acceleration should be close to 0. Indeed, that is what we see. Motion diagrams do not always have to be on a straight line. For example, supposing Tarzan steps off a branch, holding onto a vine, and swings in an arc. Or, if you prefer a slightly less complicated example, think of a pendulum swinging back and forth. When Tarzan starts, since he has just stepped off the branch, his velocity is pretty small, and thus the spacing between the dots is pretty small. But as he swings down, the spacing and the velocity grow larger, and then as he swings back up again, they grow smaller again. Let us try drawing the velocity and acceleration arrows. Here are the velocity arrows. Indeed, we can see that their lengths are getting larger up to the midpoint and then getting smaller. However, unlike previous examples, we notice that the direction of the arrows does not stay constant. The direction of v23 is not the same as the direction of v34. Now, what would the accelerations look like? Here, there are two factors affecting the acceleration. Not only is the length of the velocity arrows increasing during this part and decreasing during this part, but the direction is also changing. and the acceleration arrows need to take that into account. However, our procedure stays the same. The acceleration is simply the difference of two consecutive velocity vectors. So for example, if I do v34 minus v23, I will get the acceleration at point 3. What would that look like? Well, the acceleration would need to point like this a little bit in order to get the length larger, but it would also need to point up a little bit in order to change the direction. The simplest example is here at point 4. v34 and v45 have roughly the same length, but the directions are different. v34 points to the right and down. v45 points to the right and up. Thus, to change v34 to v45, we need a vector pointing up. We can illustrate this in a bit more detail. Remember, we are trying to find the difference between two consecutive velocity vectors. That is, we are trying to do v45 minus v34. To do this, we draw vector v45, and then we draw the negative of vector v34. This is minus v34. If we now add them, if we add these two vectors, we now have v45 minus v34. The resultant, delta v, points upward. This is the direction of delta v, the change in velocity, and is thus also the direction of the acceleration at point 4. You can see that initially the main effect of the acceleration is to increase the length of the arrows, and it still mostly points along the direction of the velocity. But as time passes, it points more and more perpendicular to the velocity, and thus it is changing the direction. At this point, the speed does not change, but the direction does. As we go further up, we see the accelerations now change the direction less and less, but are now decreasing the velocity by pointing in the opposite direction. This is an idea that we will revisit when we come to 2- and 3-dimensional motion. But in this video, we will now continue on with 1-dimensional motion. The main point I want you to take away from this, though, is what information is contained in the motion diagram, that is, how starting from position and time you can get an idea of the velocity vectors and the acceleration vectors. I also want you to remember that velocity is related to the change in position and is a vector, and that acceleration is related to the change in velocity and is also a vector. Motion in one dimension means motion along a line. And for simplicity, we will consider simply straight lines, like the x-axis or y-axis or z-axis, or some other straight line. For now, though, I will consider the motion to be along the x-axis. In this case, position is given by just a single number, which is x, the x-coordinate of the position of the object. The velocity now has only a single component, the x component of the velocity, which is called vx. And as before, this is related or defined by the rate of change of position. So we can say x dot, which is a short way of writing dx over dt, that is the rate of change of x, is v sub x. Similarly, we can look at the rate of change of vx, and that gives us the acceleration in the x direction. We can also write this as a double derivative of x with respect to time. Let us look at some examples of one-dimensional motion. To describe it accurately, we first need to set up a real line. This allows us to put precise numbers to positions and velocities and accelerations. Here's our origin. The positive x-axis is chosen to point to the right and the negative x-axis to the left. If this is the position of the object, we can say that its position has a negative value at this time. Its value is -5. Here is a motion diagram next to this axis. Remember, the 0, 1, and 2 tell you the order in which the particle's position changes. What can we say about this motion? We can say that during all these times, the position is negative because it is on the left side of the origin. We can say that the velocity, however, is positive. Why? Because the velocity arrows are pointing to the right, that is, in the direction of the positive x-axis. Even though the positions are on the negative side, since the position is becoming less negative, notice how it's going from -5 to -4 to -3, the position is becoming less negative. That is, the change in position is positive. After all, to get from -5 to -3, you need to add +2. Since the change in position is positive, that means the velocity x component, Vx, is positive. Or the velocity arrow points to the right, which is the direction of the positive x-axis. What about acceleration? Well, we see that the spacing stays fairly constant, and so the velocity must be staying fairly constant, which means the acceleration is 0. Here's another example. This time the spacing does not stay constant. The position during these times is negative, but is it getting more positive or more negative? We can see that as time passes, it is getting less negative, that is, more positive. Since the change in position is positive, that means the velocity is positive. Or, another way of putting it, the velocity arrows all point to the right, which is the positive x direction. Now, what about acceleration? Which way do the acceleration vectors point? We notice that the velocity arrows are getting longer and pointing more to the right. So the change in velocity points to the right, which is the positive x direction, and so the acceleration points to the right. Another way of thinking about this is looking at this ratio. What acceleration is asking is, as the time changes, how does the velocity change? If dt or delta t is positive, that is, if time is increasing, is delta v negative? Is the velocity decreasing? Or is delta v positive? The velocity increasing? In this case, we see that the velocity is getting more and more positive as time passes, and so the acceleration is positive. What about in this case? Once again, the positions are mostly negative. What about the velocity? The velocity arrows now point to the left, that is, they point in the negative x direction. So the velocity is negative. And the acceleration? Well, what is happening to the velocity as time passes? Are the arrows getting more negative? We see that the arrow initially is a large negative number, but then it becomes a slightly smaller negative number and a slightly smaller negative number. I'm looking at the differences. And so these arrows which are pointing to the left are getting shorter and shorter. In other words, the difference between these arrows, v after minus v before, points to the right. Or, as delta t is positive, as time increases, delta v is also positive. Why is delta v positive? Because we start initially with a very negative velocity, but we end with a smaller negative velocity. So the velocity is becoming less negative. In other words, it is becoming more positive. So as time becomes more positive, the velocity becomes less negative or more positive. But positive over positive, the ratio is positive. And so ax, the acceleration in the x direction, is positive. Another visual way of thinking about this is to think about the force acting on the object. We know that force and acceleration are connected by the equation F net equals ma. If the force points to the right, so does the acceleration. If the force points to the left, so does the acceleration. You can imagine that as this particle moves to the left, since the gaps are getting smaller and smaller, there must be a force pushing on it, which points to the right. Since the force points to the right, so does the acceleration. And since the right is the positive x direction, that means ax is positive. We have said that Vx is dx over dt and ax is dvx over dt. In other words, it is a type of ratio. And in the case of an x versus t graph, we can think of it as a slope. After all, slope is rise over run, or change in the y-axis quantity divided by change in the x-axis quantity. In this case, the vertical axis is related to position, and the horizontal axis is related to time. So the slope is related to change in position over change in time. But that is just velocity. So the slope of an x versus t graph gives us the velocity. Let's look at this region. Here, the value of the graph is positive. But what about the slope? The slope in this region is negative, which tells us that the velocity of the object is negative. This makes sense because as time passes, the position is decreasing. What about here? Here, the position is negative, and the slope is also negative. Again, this makes sense because the position starts at 0 but becomes more and more negative. And so the velocity is negative. Over here, the position is positive, and so is the slope. The velocity is positive because as time passes, the position increases and becomes more positive. Here too, the slope is positive, and so the velocity is positive. At this point, right here at the bottom of the valley, we can see that the slope is 0. And this represents a point where the velocity of the object goes to 0. Why does this make sense? When the velocity of the object goes to 0 for a moment, that means for a moment it has stopped moving in whatever direction it was moving in. In fact, we can see that the velocity goes from negative to 0 to positive. In other words, this is a turning point. And looking at the position, we see that is correct. The position becomes more and more negative until it reaches the most negative point that it does, and after that it starts going back. So, in terms of the motion, it's first heading in the negative x direction, slowing down, coming to a stop, and then swinging back in the positive x direction. All this information is contained in the graph and its slope. That is the end of this video. I'll see you in the next.